In this lesson, we're going to explore the ideas associated with network flows. We're going to look at how we can find the value of a cut in a network and how we can use the maximum flow minimum cut theorem to find the maximum flow through a network. The ideas behind network flows can be used in a variety of real-world situations. The aim is to find the maximum capacity that can travel through a particular network. Now that might be a capacity such as water or oil or gas travelling through a system of pipes. It might be cars travelling through a city. It might be people travelling through a building such as an airport or a terminal. It can also be applied in safety situations such as finding the safest way for a large number of people to exit a building at the same time using different entrances and exits. So we're going to consider this section of a network. The numbers on the arcs represent the maximum capacity that could travel along that arc in a certain amount of time. So this could be litres per second of water, for example. So we'd like to consider what is the overall capacity of the section from A to C. So we can see that the first section has a capacity of 10 from A to B. However, from B to C, the capacity is 6. So that means that overall, the flow is restricted by that second section B to C. So the overall capacity of that entire section is 6, because that is the part, that is the value that can travel along both parts. So we'd say the maximum flow from A to C would be 6. However, the section from A to B does have the capacity potentially to have a higher flow through it. However, B to C, that's saturated, that can't have a higher flow. So for each of these following situations, I'd like to pause the slide and consider what the maximum capacity is for the entire section of the network. So in this case, what is the maximum flow that can flow from A to C, given the capacities on the arcs there? So the maximum flow here is 7. It's limited by the fact that the capacity from A to B is only 7. Okay, if we add an extra arc here, just pause again and consider what the maximum flow would be from A to C in this situation. So here we've got a maximum flow of 7 from A to C via B. We can also have a flow of 10 on that direct arc from A to C. So they're travelling parallel to each other. So the maximum flow from A to C overall is 17. It's the sum of those two. Okay, we're going to add in an extra part of the network there. So again, pause and consider what the maximum flow would be for each for this from A to C. So here we have A to B to C has a maximum flow of 7, A to C directly has a maximum flow of 10, and we can also have a flow of 6 along ADEC. That is limited by the capacity of DE only being 6. So overall there, the maximum flow is the sum of those three, which is 23. Okay, let's add another arc in, D to B, with a capacity of 9. Again, pause and consider what the maximum flow would be through this network. So here we've got ABC with a maximum flow of 7, A to C maximum flow of 10, ADEC with a maximum flow of 6, but we could also increase the flow along AD slightly and then use the extra capacity D to B and then B to C. So we could increase AD to 11, DB to 5 and BC to 12. The reason we couldn't increase AD and DB any further was because that BC is restricted to 12. So if we increased AD or DB, we would then find that we had some excess flow that had nowhere to go once it reached B. So the maximum has now been reached for this network. We've got 28 is that maximum flow. Okay, again, let's add in an extra arc from B to E, see if that can increase anything. So you'll see we've got the original flow that we had from the previous example, but this time we could add an extra one, whatever we're measuring here, along AD, along DB, along BE, and EC. So that additional one along each of those arcs now increases the flow to 29. Okay, so now for some terminology. So the weights on the arcs we are calling capacities. That is the maximum amount that could flow along that arc in a given amount of time. So a node that only has arcs travelling away from it is called a source. So A is a source because all of the directed edges are travelling away from A. And then similarly, a node that only has directed edges flowing into it is called a sink. So C is an example of a sink. You can think of that as being like a tap and a plug, or you can think of it as being sort of an entrance and exit to a building. Now, any flow that we could find from source to sink is sometimes called a potential flow, because that is an amount that could potentially flow through that network. So on this diagram, pause briefly and consider which of these nodes would be a source and which ones would be a sink. So you can see that C is a source because all of the directed edges from C are travelling away from it. You see that G is another source. So sometimes we can have more than one source in a network. And we can see F is a sink because all of the directed edges are travelling towards F. And we can see that E is also a sink because again it only has edges travelling towards it. So another definition, a cut is any line that can be drawn that separates the source from the sink. So here's an example of a cut. Cuts can only travel through arcs, they cannot travel through the nodes themselves. So in this case we can see that that cut has the source, which is A, on one side, and the sink, which is C, on the other. Now I've coloured those two different colours so that we can see which nodes are on the source side and which nodes are on the sink side. Now we can find the value of a cut by adding up the weights of any arc that is travelling in the direction from source to sink going over that cut. So another way of writing a cut is to use set notation. So here we've got A in the first set of brackets, we've then got a line, then we've got B, C, D, E in the second set of brackets. So this shows that this cut separates A on one side and B, C, D and E on the other. So the value of this cut is AD plus AB plus AC, so that adds up to a total of 31. So pause for a minute and write down the name of this cut using set notation. So you can see that this cut separates A and B on the source side and C, D and E on the sink side, so it can be written like that. So if we colour the source side in one colour, colour the sink source side in the other, we can see although AD, BE and BC are all travelling across the cut from source to sink, D to B is travelling from sink to source across the cut. So if an arc is travelling from the sink side to the source side, we ignore that when calculating the value of the cut. We don't add it on, we don't subtract it either, we just ignore it. We only add up the the weights or the capacities of the arcs that are travelling from source to sink. So this cut, we would only add AD, BE and BC and AC together. So the total value of that cut is 37. So notice, although it's the same network, we haven't got the same value as the previous cut that we found. So we're now going to work out the value of all possible cuts through this network. The first potential cut is A on one side and B, C, D, E on the other. We already found the value of that, it was 31. We also already found this cut, A, B and C, D, E, so we got a value of 37 for that. So pause the slide for a minute and work out the value of this cut here. So all of the arcs are travelling from source to sink for this cut, so we're going to add up all of the values, we get 32. Next, here is another cut. Again, pause the slide and work out the value of this cut, only adding arcs that travel from source to sink. So we can see this time we've got BE is travelling from sink to source. So BE won't be included in this cut. So when we add together the value of the arcs that are crossing it in the right direction, we get 34. Next, again, pause and find the value of this cut. Value is 29. And the value of this cut, that is 30. So all of these cuts that we've found all represent an upper bound for a potential flow. So what we're saying, every time we find a cut, we are saying there cannot exist a flow larger than this number. So when we found a cut of 31, we were saying that there cannot be a flow through that network any larger than 31. When we found a cut of 37, we were saying that there cannot be a flow higher than 37. So the smaller the cut, the better, because it gives us more information. So we want the smallest upper bound possible. So in this case, the one that gives us the most information is 29, because that tells us that there cannot be a flow of more than 29 through this network. And that leads us to a theorem called the maximum flow minimum cut theorem. Now this theorem states that because cuts all represent upper bounds for potential flows, so in other words, flows definitely cannot be any higher than that number. If you can find a flow that matches that number, then you have found the maximum flow. Okay. Now, the way that this works is that the minimum of all potential cuts, minimum of all the cuts, gives us the maximum of all the potential flows through that network. So if we can find a cut that has the same value as a flow, the flow is often found by trial and error, so you just try to find the biggest possible flow you can. If you can find a cut that also matches that same number, then by the maximum flow minimum cut theorem, you have found a maximum flow. You would need to quote this theorem if you used it in a question. So if a network has more than one source, what we can do is add an extra node and call this a super source, and that links into all of the existing sources. So in this case, A and B are the two sources to this network. So we are going to add S, call that super source, and link S into A and B. We can also do the same if we've got multiple sinks. So here we've got F, G and H are all sinks for this network. So we can add a super sink, call it T, where they all flow into that node. Now we don't want the super source or the super sink to restrict the flow in any way. So we need to make sure that we give the extra arcs that we have added, so SA, SB, FT, GT and HT, we need to give them a capacity that is high enough that it doesn't restrict the flow onwards from that. So it needs to either the same capacity as the arcs that are connecting to it or higher. So in this case, we would give SA a capacity of 15 plus 9 because that is the capacity that then flows out of A. So we'd call that 24. S to B, we'd need to give a capacity of 18 because 18 is the total flowing out of B. F to T, because F has got capacities of 8 and 3 going into it, we need to have F to T with a capacity of 11. G to T, or G only has one edge, one arc flowing into it, so G to T is 7, and then HT, we're going to give that a capacity of 20. So by inspection, we're going to find the highest possible flow we can. So you would do this just by trial and error, by trying to work out different paths from S to T, adding on as big a flow as you can until you think you've reached a maximum. And then you're going to go back to the capacities. So you always use the capacities to find a cut. If you can find a cut that has the same value as that flow that you've found, then the maximum flow minimum cut theorem will tell us that we have found a maximum. So just by inspection, the values in circles there are a potential flow. So you can see that we could have, for example, 21 flowing along SA, we could have 12 travelling on AC, 9 going along AD, and so on. So when you are doing any potential flow, you need to be careful of things like making sure the capacity or the amount flowing into a node has to equal the amount flowing out of a node in order to make this balance. You also need to check the amount flowing out of the source should be the same as the amount flowing into the sink. And if you've done that correctly, the amount flowing out of the source or the amount flowing into the sink should equal the flow that you currently have going through that network. So here you can see we have a maximum or potential maximum flow of 37. We can see it's 37 because we've got 37 altogether flowing out of S, and we've got 37 altogether flowing into T. So to prove it's a maximum, we now need to find a cut that has the same value, 37. A good way to look for potential cuts that will give us this is to try to travel through as many saturated edges as possible, so saturated edges that go from source to sink. So in other words, edges that cannot be increased anymore because they already have a maximum amount going through them. So just by inspection there, we can see that this cut, so S, A, B, C, D on one side, E, F, G, H and T on the other, that will give us the cut value that we need, 37. So we can say because we've found a flow of 37 and we've found a cut of 37, then the maximum flow minimum cut theorem tells us that we have found the maximum. And that maximum is 37. So you would need to state this if you're writing this in a question. Okay, now please have a look at these questions. So questions 1 and 4 on page 84, and then the exercise 5.1 on page 78.